Okay, welcome back student. So, in our last class we started the concept of vector space, and we know from where this vector space is coming. There is a field, and over that a vector space is defined, they form ring and all these things, there is a group, the concept of all these things you know. Today I like to start more detail about how to define a space and what is the basis, what is called span and all these things, important thing. So, let us start with span, a very important term. Before dealing with this span, let me once again write the different vector notation. So, vector notation. So, there are different way to note the vector. For example, normally I write alpha 1, alpha 2, alpha n, say this is a set of vector. Now, these are different vectors. So, one vector alpha 1, 2, 3 are different vector, but now I am writing one vector alpha with different components. Say this vector alpha can be written in terms of C I phi I. This C I are the coefficient of this vector, where phi I is a basis vector. I will come to this point just to, for the time being, just you bear with me with the fact that I am defining something basis and a vector can be represented in this form. So, this is a summation form of a vector. Now, the same vector alpha can be written in terms of row or column matrix, where this C1, C2, these coefficients are there, say I2, 1 to n for example. This is called n tuple notation. Maybe we will going to use that in our next class also, but this for here, this understanding span, this is important. Another important notation also have, this is called the bra notation. This is a very important notation in quantum mechanics, but here whatever I am writing is basically the vector form, but in quantum mechanics this vector form is will be written, but as a they will use as a state vector, they call a state of a function, but essentially the mathematical structure is same. Okay, now after having the knowledge of how to write a vector in this form, however the basis and all these things is still there. Now go to our old topic, span. What is the meaning of span? Okay, so let us take few vectors of alpha 1, alpha 2, alpha n, which belongs to some vector space V. So, some vector space is there, and these are the few elements, n elements. There are maybe more than n elements, but I am taking only the n elements of that. If I make a linear combination of that, linear combination of the set, I put this set as S. That means S is a subset of the given vector space V, which contain the vector alpha 1 to alpha n. So, the S contain basically alpha 1 to alpha n, this vector. I put a set, this set is basically the subset of the entire vector space V, and if I write S as a subset of entire vector space of V, there are few elements that is inside the subset S, which is also belongs to the vector space V, and linear combination of S means I will take all the vectors and write it as this way. all the vector which belongs to S I take and write C1, C2, C3, Cn in this form. This is C1, C2, C3, Cn are real quantity, real scalar. It may be imaginary also, it is not necessarily it is a real. If the vector space is real, for the time being let us take a real vector space. So, this quantity may be real, for the time being I am taking real vector space. So, that means the field over which the vector space is formed is a real field. So, this quantity is taken from the scalar quantity and this scalar is a real quantity, but essentially this is a scalar, this is not a vector. This linear combination, if I make a linear combination, if I say it, I am taking the value and make a linear combination, it will look something like this. I will take all the vectors multiplied with this constant and then make a summation over that. So, this is linear combination. Now, this linear combination is called the span. So, span of S, that means I am taking few vectors from the given vector space and make a linear combination over that, then span of that set, when I make a linear combination, then I called a span of these things. So, span of these things is not equivalent to all possible linear combinations. Span of S means all possible linear combination. That means whatever the value C1, C2, Cn I like, this is basically forming a span. So, let us take some example. This is a rough, this is something which is just the definition. Now, if I write, if it is a definition, now if I write in a mathematical form, then say alpha 1, let us take R2. R2 means all the vector that I am taking will be in 2D. So, that means alpha 1 and alpha 2, these are two vectors that I can take from the entire vector space which belongs to R2. So, if I write say alpha 1, one vector 1 2 and alpha 2 another vector say minus 1 1, then these two vectors I am taking from R2 and form a set where alpha 1 and alpha 2 are there. Okay. Now, I am saying that is it possible to write a vector, what will be the linear combination? So, let me find out the linear combination. So, one linear the most general form of the linear combination is this one. This is the linear combination LC of the vector. This is the linear combination of the vector. These two vectors are giving to me, I have a linear combination and then C1, C2 I multiply. Now, it is my choice what C1, C2 value I will take. So, let us take C1 as 1, C2 also 1. If I take C1 equal to 1, C2 is equal to 1, then if I put here, then what value I will get? 1, 1, 2 plus 1 minus 1, 1. As a result, I am having something like 1 minus 1, it is 0, 2 plus 1, 3. 0, 3 is a new vector and it depends on what value of C1, C2 I choose, I can start generating the new vectors all time. If I take, for example, if I take C1 is equal to 2, C1 equal to C1 equal to 2, C2 is equal to say minus 5, I will get a different vector. If I take this is 0, this is 1, I will get a different vector. Whatever the possible value you imagine, if you put this value, you will start getting every time new and new set of vectors. This is merely an example. So now the next problem is, the next thing is, this is the linear combination of these two. Now I am saying that I want to find a specific vector x and y out of the linear combination. A specific vector x and y are, I will choose what will be my x y. Previously what we are doing, we are just choosing C1 and C2 and I am getting a new vector. Now I am saying the other way, that I am going to choose C x and y and try to find out what is the value of C1 and C2. So let me do that. So quite simple. So C1 minus C2 will be x, 2 C1 plus C2 will be y. This is my equation, the first equation. So now if I try to solve that, mind it, I need to find out what is my C1, what is my C2 when x and y is given. So it is not that x and y I try to find out, I try to find out C1 and C2. So I need to solve in such a way that I will have C1 in terms of xy and C2 in terms of xy. So if I add this, I will have 3 C1 is equal to x plus y. That means C1 is equal to x plus y divided by 3, this quantity. And now if I put, if I multiply these things with 2, so this is one solution, and if I multiply this with 2, you can do in anyway, you can do in another way also. So C2 is C1 minus x. So C1 is this, x plus y divided by 3 minus x, it is 3 y minus 2x C2. So I can have a value of C1, I can have a value of C2 both in x and y. So if my x and y is given to me, then I can readily find out what is my C1 and C2. So let us do these things. So let me write it somewhere. What is the value of C1? So C1 is your x plus y divided by 3 and C2 is y minus 2x by 3. Okay, so up to this it is fine. Now I need to figure out the value of C1 C2 for a given xy. Now let us take this is 2 5. So I will try to find out the value vector 2 and 5 in terms of linear combination of two vector 1 2 and minus 1 minus 1 1. My result will be 2 5. So that means my x is here 2, y is here 5. So C1 will be x plus y, that means 5 plus 2 7 divided by 2, and my C2 is y minus 2x, that means 5 minus 4, that means 1 by 3. This is it really correct? Cross verify. 7 by 2 minus 1 by 3, so it should be 2 7 by, okay, no, 7 by 3, this is I am making. So this is x plus y divided by 3. So x is 2 7 2 by 3, then it is coming 7 by 3. So 7 by 3 minus 1 by 3, it is 6 by 3, it is 2, it is 2. Then y minus then the next one is 7 by 3 multiplied by 14 by 3 plus C2 is 1 by 3. So, it is 15 by 3, 15 by 3 means 5. So, I will 5. So, that means I can generate from these two vector, I can generate whatever the vector I like in R2. That is the most important thing that we figure out with this treatment. What is these two vector? These two vector I took from R2, this is the arbitrary vector, but this two vector has some power through which if I make a linear combination of that, I can generate any vector I like. X y can be anything. So, I can generate any vector if a given vector is to me. So, I can find my C1 and C2, so that I can generate any vector with this linear combination. So, for this alpha 1 alpha 2, so I can write span of this S is equal to the entire vector space R2. We called it this vector alpha 1 and alpha 2 span the entire vector space. That means, give me 2 vector, I make a linear combination and I can generate any vector I like. But is it always true that any arbitrary vector if you took and you will generate the span of these things, it will going to generate a span. These two vector span of these things is basically the entire vector space it will do. But it is really true for this or any other things, other relation is required for that. That is a very important thing. So, let me change these things. Let me took another vector alpha 2, which is 2 4. This is also another vector. They will have this and these two vector I can take from R2. Now, try to find out whether these two vector can span the entire vector space or not. So, that means C1 1 2 plus C2 2 4 is equal to x y. I demand that I will solve this equation. From here I will have one equation C1 plus 2 C2 is equal to x, 2 C1 plus 4 C2 is equal to y. I demand that I will solve this and I will find some unique C1 and C2, so that any vector is given to me I can figure out. So, now if I do try to solve that, you will find, let me solve it, these two equations. What I will do? I will multiply here these things and these things, from these things and this thing I do not need to do anything. If you want to solve that, you will not going to get any solution over that, because these things if I multiply 2 over that, then I will have a relation 2 x is equal to y. This relation I will end up. If I want to multiply, say if I multiply 2 and then if I, when you multiply this equal 2, then if I try to solve, you will never find a solution of these things. Why it is that? Why it is like that? You merely have a relationship between these two. So, that means this relation only you can get, but not a unique solution. That means you can't have any arbitrary value of x and y for which C1 and C2 you can define specifically. Why it is that? It is because, the reason is because these two vectors alpha and alpha 2 is not linearly independent. A new term is here which is called linearly independent. I will describe this term later, but for the time I am just writing this. What is the meaning of linearly independent and dependent? Very simply I can understand that I can write alpha in terms of alpha 2 like this. If I take a half of that, if I write one vector in terms of other vector, then these two vector is called linearly dependent vector. So, this two vector is linearly dependent. This term linearly independent I wrote previously to show that whatever the vector you are taking to make a span, they should have some relationship between them to span the entire space. You find that for these two vector, even though they are forming a linear combination, but this linear combination cannot leads to any vector I want in the vector space. That means there is a restriction between these two vectors, and this restriction is they has to be linearly independent. If they are linearly dependent, then from that span I will not able to whatever the vector I will have, if I make a span or make a linear combination of that, I will not get a vector, any vector in the these things. So, they will not going to span. So, these two vector not going to span the entire vector space. The linear combination will be there, but they are not going to span the entire vector space. Okay, so now I will go back to this. You can do that for other dimension also. So, I should mention here, for example, R3. Say I will have one vector alpha 1, say 1 0 minus 1, alpha 2, another vector say 1 0 0, and alpha 3 I have minus 1 0 1. These three vectors can also potentially form a span, because if I make a linear combination of that, this is a homework, please do that. For R2 I did, for R3 you should do that. This is the linear combination of the vectors. These vectors I make a linear combination, and my demand is that linear combination can leads to any vector in R3. Now, if this is true, then I should have a relationship between C1, C2, C3 to X, and I can write my C1, C2, C3 in form of X, Y, Z. If I do, then I have a recipe that what should be my value of C1, C2, C3, so that I can generate any vector in my hand. So, this is the same treatment that we have already done for 2D case, which was simpler, but here is also simple. It is not very difficult thing, just need to find out this. So, let me write down the equation for that also to make things easy. This is one equation you have. The next equation, C2 is 0, C2 is 0, C3 is 0. Okay, now there is a problem that I will have something 0 0 0. So, this vector may not be okay. Let me have another equation. So, make it change, because if we have all 0 in the middle, then I shouldn't have this vector. First I need to check whether they are linearly independent or not. So, first equation is that I will show in maybe in the next class. Second equation is C3 is equal to Y, and third equation is C1 is equal to minus of Z. So, it is easy, it is quite easy. C3 you can readily understand, C1 you can readily understand, and from that C1 and C2 you can readily find out what is your C2. C1, C2, C3 you can readily find out with the X, Y, Z quite easily in fact. So, next I will show few things. So, in R2 these are my natural choice. Why this is natural choice? In R2 I mentioned the span is two vectors, any two vectors and if I make a linear combination of that two vector, I will generate a new vector. So what I did, I take say some vector 1 1 and then 1 minus 1 and then make a linear combination and try to find out what is in the right hand side and so on. But if I take this vector with this form 1 0 and 0 1, life will be much simpler. So let us find out. So C1 1 0 plus C2 0 1 is my x and y. This is my equation. This is a linear combination, C1 multiplied by vector plus C2 multiplied by vector. This is a linear combination, and because of the linear combination I will get a new vector, I will have a new vector. If I have a new vector, then I can say this new vector have the value of C1 and C2 in terms of new vector coefficient is simply x and y. So there is no need to make a solution. So readily I can find my C1 and C2 if I use these two vector as my spanning set, the vector of my spanning set. So any vector, that means any vector say 2 5, I can write this 2 5 as 2 multiply 1 0 plus 5 multiply 0 1, as simple as that, minus 1 3, I can write this vector that 1 0 3 0 1. So readily I can expand a vector in terms of this spatial vectors. This spatial vectors is called this spatial vector is called natural basis. The word basis is still unknown to us. We will do that in the next class, but please remember this is called the natural basis. You can have these things for 3D also, 3 dimension. It will be something like this. If you make a linear combination C1 plus C2 plus C3, you will simply have a vector x, y, z. Whatever the x, y, z you have, the same value of C1, C2, C3 is there, as simple as that. So with this note, I like to conclude here. So one important thing we learned today's class, that is span. Span is what? A vector space is given to you. You choose certain vector and make a linear combination of that. When you make a linear combination of that two vectors, then you will find that you can generate any vector you want from that chosen set of vectors. So if it is possible to generate any vector from that chosen vector by making the linear combination of them, then we can call this vector as a spanning set. And now we find that there is some unique choice of this spanning set vector, which we call the natural basis, using which you can generate the vector very nicely, so that you don't need to know what is the relationship between C1, C2, C3 with x, y, z and so on. So that means you have some kind of spatial vector which is a preferable thing. In the next class we will learn how these things are there, and also we need to know one important thing, that how this spanning thing will span 2D to 3D to 4D and so on. It is not necessarily that you will take two vectors and span 3D. So it is not possible. I will show in the next class. So with that, let us stop the class here. In the next class we will start from here and trying to find out what is the meaning of basis, which is much more important. With this, I would like to conclude the class here. Thank you for your attention.